So, couple quick things. So, next week, I have to travel Monday, Tuesday, Wednesday, so I will not be here for office hours. However, there's going to be a TA, extra TA office hours on Thursday. Because I'm going to be out, Rebecca, up at the back, hello everybody. You guys know her from the TA. She's one of the TAs for the course. She will be standing in. So the lectures are all prepped. She will be giving those lectures. She is a junior teaching, let's see, aspirational junior teaching person. So please give her your attention. She will tell on you guys, so please be nice. But everything else will sort of proceed as normal. See you guys on Friday for that part. I will also be recording a midterm review. So basically all the other components and stuff that you guys need for prep up, I'll have that as a recorded video and I'll post that part up for you guys to see at that part. Remember, during that time, do still please submit your design question up onto Piazza and then we'll make it up onto the midterm. So last class, we opened up about aromaticity. So this is introducing benzene and the unusual stabilization that come along with it. The other two parts of this is we also introduced anti-aromaticity, so that's unusual reactivity as a result of it, and also non-aromatic type compounds. And we just started to talk about how aromaticity, or having the ability to make an aromatic compound, can actually be coupled to reactions. So a molecule on its own, if we have our sort of those 4 rules, we can say if it's aromatic or not. However, we can couple a molecule to a reaction to either become aromatic or to break aromaticity. So certain things like some nitrogens, their lone pair, is really not accessible as a base because you would have to sacrifice aromaticity as a result of it. Also, there's ways to do reactions to change a molecule's parameters, if it is aromatic or not. So if you look at these 3, I'd like you to classify them. Are these aromatic, anti-aromatic, or non-aromatic? Take 1 minute with the person next to you. Come up with 3 answers, please. Okay. All together, let's do them 1, 2, 3. What is your decision on that one? Anti-aromatic, aromatic, non-aromatic? Okay, once again, it is what? It's why. What does it not do? What's wrong? Yeah. Well, it's cyclic. Yeah, right there. That's an sp3 center. There's no p there's no p orbital available to have extended conjugation. That's going to break your aromaticity. So that's just a non-aromatic molecule. Okay, guy here. That is aromatic, anti-aromatic, non-aromatic. Anti-aromatic. It is cyclic. It has the p orbitals. It's planar, except this is 2, 4, 6, 8 electrons that violates our 4n, not the 4n plus 2. That is an anti-aromatic molecule. Yeah?
On the first molecule, because if that was a carbocation, it would have 10 electrons in the structure. Does that mean that that hydrogen is very acidic?
Okay, yeah, good question. So on the first molecule, the center I've circled here, this is an sp3 one. There is a hydrogen here. And yes, if you were to jettison that hydrogen, get rid of it, you would make an aromatic molecule, which means, yeah, it's going to be way more acidic than normal because it forms a very stable compound. Absolutely. That's a good point. So this one here, aromatic, non-aromatic, anti-aromatic. Aromatic because 4n plus 2, where n is equal to 0, there's 2 electrons. It is cyclic. It has 2 electrons. Every carbon in your 3-centered ring, including the carbocation, has a p orbital. So all of these are sp2 carbons. That is an aromatic molecule. Absolutely. Good. All right, A, B, C, D. Which of these is not one of Huckel's rule? Oh, wow, that was quick. So everybody together? It is? Yeah. Neutrality is not, it's not Switzerland. You can see this where molecules can be aromatic even if they're charged or they're diradicals or other components. Being neutral is not the characteristic. It's really about the geometry, the orbitals that are involved, and whether or not we have resonance around. Okay, so today we're going to talk through some of the reactions that have this. So basically, now we've got this concept of aromaticity. It imparts special reactivity not only at the molecule itself, like in the benzene ring, but it also changes at the periphery. So we're going to talk a little bit about reactions at things attached to benzene and how they're a little bit different. These include things like our phenol and phenoxide reactivities, as well as benzene derivatives at what we call the benzylic center. That's the CH2, or the carbon, attaching to an aromatic ring. Okay, so last time we started talking about a phenol and the relative properties of the phenols. There's three reactions we're going to talk through. A phenol on its own, think of it like an alcohol. It's a little bit like an alcohol. We have an acidic proton on that oxygen, which means we can relatively easily deprotonate it and create an O-, like a phenoxide. Something that is like an alkoxide, or MEOH becomes MEO-, which means it's going to be a nucleophile. We can use it as an oxygen-centered nucleophile to do certain kinds of reactions. So property one, we're using the relative acidity of this center that makes a stabilized anion, right? The O- we form here is more acidic than a typical alcohol because that O- is going to be delocalized around the ring. We can use it as an oxygen nucleophile with good electrophiles, like that center here, doing an SN2 type reaction. So very simple bases like potassium carbonate, a little bit of heat, and you can get this, what we call Williamson ether synthesis. The reason we're calling that, remember, an ether is this molecule here, a carbon on either side of an oxygen. So this is how we do ether formation, starting with a phenol, creating a phenoxide. So the intermediate we're generating here will be the nucleophilic O-, and then this is just an SN2 chemistry of that nucleophile displacing a good electrophile, like a good leaving group like our chloride. So what we're doing there is we're forming this bond right here, the oxygen to electrophile bond. So property number one, most phenols act like oxygen nucleophiles in the presence of simple weak bases. That's the first part. Now, we cannot do the other side. What I mean is, if I took a molecule like methoxide, that's OMe, right, and I want to make an ether here, where what I'm doing for that ether synthesis, my nucleophile is this OMe part. That means this is my nucleophilic portion. I'm trying to make, in that case, this OR bond. It's the one where the oxygen is actually installing into the ring. This is not a typical SN2 reaction. Why not? If I'm taking an O- attacking an sp2 halide center, this is not SN2. Why not? Yeah, SN2, or an sp2, or sorry, an SN2 reaction must happen at an sp3 center. The nucleophilic substitution, if you remember, SN2 is nucleophile comes in, we have a tetrahedral intermediate that is ejecting some leaving group. We have that sort of five-centered tetrahedral intermediate as a single transition state. There is a way this reaction does work. You can do what I'm showing you on here, but this is just not classed as an SN1 or an SN2. This is something else that is very special. We call it nucleophilic aromatic substitution. We're going to come back to this. But the thing I'm classing off is, if you are trying to make that bond right here, you need some very, very, very specific conditions. Most importantly, this group down here has to be in place to do this kind of substitution. You remove that nitro, this will not work at all. And again, we're coming back to it. But all I'm trying to emphasize for right now is, in a Williamson ether synthesis, we're making the bond from the phenoxide out to another carbon. We are not making this bond. We don't make the oxygen to aromatic bond. That's a special other reaction because that requires us to attack an sp2 center, not an sp3 center. So we're going to talk about this a little later, but the products you can get here. Basically, the thing that we're looking at is phenols in this capacity act like very good oxygen nucleophiles. Simple to form, O- is relatively stable, attack normal leaving groups is what we're doing. That's how we form our ethers. Now, once we've made the ether, because the O minus is a relatively stable anion, it is a good nucleophile, it can also act like a leaving group under the right conditions. So this is how we go backwards after we've made our ether. An ether like this might be formed from the Williamson ether synthesis we just showed, where we would do a nucleophilic attack at that center. But now if I want to cut it back, go back to my phenol, I can, but it requires strong, strong, strong acid. So usually we're going to go in with something like HI or HBr to do this. And by doing that, what I'm doing is clipping this bond here. It allows me to sort of unmask this oxygen again, and I'm breaking the oxygen to carbon bond. How do you think this happens? If you had to guess what's going on here, like you look at your products, the iodide is ending up at my center over here. I've broken this bond. If you had to kind of class this, what does this kind of look like? Sort of. Looks like SN1, right? Super strong acid, HI, and you're doing this. So basically what has to happen here is we're probably going to end up protonating my oxygen first. So now what I've done is taken that oxygen, made into a very, very, very good leaving group, and then I've got I minus floating around, which is acting basically as my nucleophile. Now you can think of it as SN1 or SN2, but really this requires you to first of all protonate that oxygen, help it as a leaving group, and then capture it with what is generally a terrible nucleophile, right? There's two reasons this is possible. The phenol you're making is very stable, so you're paying the price by making a molecule that is a stabilized product. So energetically, the whole system is actually allowed. This is not very favorable. Like you can do this, but it usually requires a heck of a lot of HI, time, and high concentration and temperature. It's also the type of thing that if your molecule does not have anything, has something else that might react with HI, this gets very, very difficult. But basically, all we're trying to emphasize here is you can both make the oxygen to carbon bond by SN2. You can then unstitch it with very, very hot, strong acids like this as well, too. Yes? You can just do it. Again, usually wouldn't form a primary carbocation. That would be more SN2-like, where you'd still protonate on the oxygen, and then the iodine is probably coming in at the same time as you're breaking it. Rather than here, you might make a secondary carbocation. But think of it still in the same class as SN1, SN2. The weird thing about it is, usually your strong mineral acid, like HBr, HI, the halide is acting as your nucleophile to close this sequence. That's why you're making that as your byproduct. So then we're going to talk through that, including a longer mechanism after class. The last thing we can do with phenols is we can use it in what's called this carbonylation chemistry. So here, if we made a phenol and we deprotonate it, we make our phenolate, or the phenol anion, like this. Again, that's just sodium carbonate, can form that very easily. Now, if I look closely, let's say I'm going to zoom in. I know, right? What does that functional group look like? It's an enolate, right? So what we're trying to emphasize is that piece on its own, like yes, it's part of an aromatic ring. Yes, it's part of aromaticity. But when you deprotonate the phenol, it can act as an oxygen nucleophile for simple electrophiles. That's usually when you're making your ether synthesis. However, it has this other property. It kind of acts like an enolate. Since it's like an enolate, if you take another pi electrophile, like CO2, you're actually going to do what looks like an aldol condensation almost. Here, it's possible to take that anion, and we're doing something like bloop, bloop, right? It's a negative charge goes down, and we're attacking there. What that lets us do is I'm forming a carbon-carbon bond between my sp2 center of my enolate and my sp2 center of my carbonyl. We'll go through the mechanism after class about this. This is actually used commercially. This is how we make acetylsalicylic acid or aspirin. So you take phenol and you can actually stitch in CO2 in this way. This is also not a solution to greenhouse gas, unfortunately. It takes so much energy to push this in here. It's not really good at capturing it. You'd have to dump them. You'd burn a bunch of coal to get a bunch of energy in order to add CO2 back into it. So it's not that solution, but it's interesting because the phenol is actually nucleophilic enough as a carbon nucleophile in order to catch CO2 this way. Yep. If you heat the product, will it decarboxylate? Yes. Like, again, this is retro. The only reason that this works is because usually you're under an atmosphere, high pressure CO2, which drives the equilibrium to your product. If you had no CO2 in the atmosphere and just heat it up, decarboxylation is possible at those high temperatures as well. But, but how you're getting it to your product is, again, Le Chatelier. Enough CO2 will help to drive you to that product. Yes? Yes, right? But the thing is, this is what we're going to talk about with the next phase, what we call nucleophilic substitution or aromatic substitution. You could hit it again because it still has enolate activity. What do you think happens to the nucleophilicity of this carbon after you've added a carboxylic acid? Basically, is a carboxylic acid electron donating or withdrawing? So it's not easy, but you can do it. What we're leaning up to, guys, has everybody heard of TNT? Hands up if you've heard of TNT. Okay, hold on, I need a picture. You guys are on a list now. Trinitrotoluene is taking toluene and adding these nitro groups. Every nitro group is a deactivator. So the next addition is possible, but you got to hit it harder and harder every time. So yes, you can do one more addition, but it gets harder than the first time. Possible, but again, higher temperature, more CO2, more time. So what's happening here is phenol has this kind of property. It's just like the enolates we saw before. They are oxygen nucleophiles, they're oxygen minus, but because of this delocalization, they have centers of nucleophilicity in this pattern here. And this follows the sort of, again, if you chase down where that O minus goes, you draw out every resonance structure. You have the oxygen nucleophilicity. That's what we take advantage of, a simple sp3 alkylation. We have carbon nucleophilicity. That's our CO2. Pi electrons, like or pi electrophiles like CO2, prefer to attack over here. We also can attack in this position here or here. Now, what do we call these? This is our ortho. This is your what? Meta, and this is your... So notice that with carbonylation or CO2 addition, it will only ever add orthopara. Because having that negative charge there means that you're only going to have nucleophilicity. You're only going to have these specific regioisomers. You're not going to just decorate anywhere you want. It will only add in these ortho positions or the para position. So, which is more favored? This is actually interesting. You can take this chemistry, and if I run it, if I take phenolate and I add CO2, it can add once in either two positions. Now look at the two pKa's. You're starting with phenol, pKa 10. Remember, that's like my stabilized alcohol. And then I'm making salicylic acid or the para-salicylic acid, what we call sort of para-hydroxybenzoic acid. Look at the two pKa's of those two ones, salicylic acid versus the hydroxybenzoic. Which of those two anions is more stable? So let me ask a different question. If they were in their protonated form as the carboxylic acid, adding a proton, which is a stronger acid? Salicylic acid or hydroxybenzoic acid? Why? Lower pKa, more acidic. So if it's a lower pKa, more acidic, this is our more acidic acid. When it's in the acid form, this is the conjugate base of that acid, which means that is the more stable anion, right? This is our more stable anion here, which means if I have this equilibrium set up where it can go in the 4 position, back and decarboxylate, into the 3 position, which way does the equilibrium go? To the left or to the right? It's going to go to the most stable one. It's going to come over here, right? So why? What's causing that to happen? This will be your more stable. That's the direction your equilibrium is going to go. You're chasing stability. So the pKa, the anion that we're actually doing here, the pKa is informing us about the relative stability of the anion. Since that acid is more stable, its anion is that anion is more stable. It's coupled to the stronger acid. Why do you think the like this ortho substitution is better than the para? Yeah. Okay, so you're saying, okay, your theory was you have an electron withdrawing group near to the hydroxyl. But remember, we're talking about the stability of that anion. The anion is over on the carboxylate, not on the OH, right? So don't think that's it. It's not geography there. Yeah. Well, you have the same number of resonance structures in both cases, right? The two substitutions, if you draw them out, will have that same point. This is a little more geography, yeah. I wouldn't call it induction, but you're getting closer. If I redraw this, like let me redraw this one like this. If we draw the phenol compound, OH, and we've got this, if I have my negative charge like this, through space, I have a hydrogen bond I can form where that phenol is donating to that O minus. Basically, this is like a through space help where the phenol's OH is helping to kind of cap or partially share that proton between your carboxylate and your phenolate. So having this just gives us, basically think of it we're by geography. This OH being nearby is just helping to add or partially donate to satisfy that O minus. This is a geography part. But basically, it's these sorts of features that not only the position, but the relative substitution helps with stability on these different parts here too. Again, this is not something we'd want you to be able to do by inspection. This is why we're showing it to you now, saying here are these other features that help you with these stability parts. So that's what happens with just generally these carboxylations. The last reaction I want to show you is this oxidation reaction. Phenols on their own can be treated with this reagent. This is your sort of like Jones type reagents or like chromium oxidizers. These, what they do is they actually add an oxygen to the ring. And if you notice, they add the oxygen in the 4 position and 2 position. So what does that tell you about the behavior of this phenol? Is this phenol acting like a nucleophile in order to pick up this oxygen? Since it's substituting in the 4 position and 2 position, it's kind of taking advantage of the same negative charge pattern you're seeing over here. So this is just saying that these kind of chromium type oxidations, what you're kind of doing is you're taking an O plus kind of reagent and you're using the nucleophilicity at position 4 and position 2 to add an oxygen in. Does anybody know or have heard of these hydroquinones or quinones before? Biochemistry, you should probably be recognized. This is your electron transport chain, right? Like this is how your body does reduction oxidation with things like NADH handoff. I sensed that there was a biochem midterm recently. Yeah. Okay. Let's move on. So those are the basic reactions we have with phenols. They are nucleophilic. They're electron rich. And we can use conditions where either oxygen nucleophile, so that's like our sp3 attack. We can do them as 2,4 nucleophilic addition. That's mainly CO2. Or we can do direct oxidation to get us to our quinones and stuff. The next one is, okay, if I have an aromatic ring and I'm going to functionalize at what we call benzylic centers. Now remember, benzylic positions, those are the carbons adjacent to the ring. They're the first carbon as you branch off of the ring. And there's a couple of very important reactions we can do because what this lets us do is modify around the environment of the ring. And these are specific to the benzylic position. They don't work everywhere on hydrocarbons. They only interact with CH2s or like sp3 centers adjacent to the benzene ring. So first is what we call benzylic bromination. Now under these conditions, you're using a reagent called NBS. You probably have seen this guy in like 203, 123, stuff like this. Its job is to act as Br+. It's an electrophilic bromine reagent, but it's also a very good reagent for things like Br dot. These are also considered as radical sources of bromine, right? These guys are acting as a bromine atom donor. Now, if you take a normal molecule and you just hit it with NBS, not much happens. You take a benzylic molecule, NBS, also not much happens. What you need is that right there, benzoyl peroxide. You guys recognize this? You may have seen it in like polymer type chemistry. That thing is a radical initiator. Its job is to start making radicals, to start a radical chain process. Benzoyl peroxide, anytime you see peroxide, their job is to make basically single electrons who then go through and rip off protons. What's happening here is benzoyl peroxide is going to make a what we call benzylic radical. Its job is to take the hydrogens that is just next to the ring, rip off one of those hydrogens under what we call a homolytic cleavage. This is not making a carbon plus or a carbon minus. It's removing H dot. And when you do that, you leave behind carbon dot. This is possible because that carbon dot, that center, that's a very high energy compound, right? Taking a radical in a position is not the happiest thing in the world, but that is a radical attached or right next to your aromatic ring. It has a ton of conjugation, which means it's a relatively stable one. If I had to make a carbon dot, that's not usually easy to do, but because I have this benzene ring next door, it's now accessible. Think of it just like making a tertiary carbocation. Not a very stable intermediate, but because I have all that stabilization around it, I can access a tertiary carbocation. This is the same thing here, where a normal carbon radical, not super accessible, but by having this aromatic ring next door to it, I can form it. The benzoyl peroxide is reactive enough to make this guy. What that lets me do is I can install a bromine into that position. So what I'm doing is an atom swap. I rip off an H dot and I install a bromine. Yeah? Why do you use carbon tetrachloride? Very good choice. Now again, does anybody have an answer to that one? Have you ever encountered this? In general, radical chemistry is pretty reactive. What you're doing is you're taking a reagent like benzoyl chloride, you're making a radical. That radical will react with anything it can get its hands on, and the number one thing you're going to bump into is solvent. Carbon tetrachloride is resistant to many radical processes, so usually this is a reaction that's done where the solvent there is invisible to the reaction, to the radical chemistry. That's one of the downsides is, has anybody got to play with carbon tetrachloride? Yeah, you guys are... I have burns from carbon tetrachloride. They used to use it as a dry cleaning agent. I am so thankful for all of you guys' health and non-cancer futures that they don't do that anymore. This is not a very, very stable solvent to use. It's actually very difficult. There are actually old professors that have secret bottles of carbon tetrachloride that they don't tell the EPA that they still have because they're supposed to be gone. So it's kind of like one of these things you can hand down from like your master. So the one downside about this reaction is it's difficult to control. You're trying to put one bromine in, and most importantly, the bromine gets installed where there used to be a benzylic CH. So what we're saying is in a molecule, you're looking for the centers, the carbons that can react, is a benzylic CH. Once you have a benzylic CH, now you're going to install a bromine in that position. So if you look at this structure here, this is my molecule. I'm going to hit it with NBS, carbon tet, and some radical initiator, benzyl peroxide or something like this. Remember, this guy's job is to just start the process by making radicals that can extract that C dot. So in this molecule here, step one, I need to identify what centers are benzylic hydrogens. So I've got a benzylic center here. I got a benzylic center here. Red versus green. Where can you install a bromine? I cannot touch the green center because it's carbons. The carbon-carbon bond is strong enough, it will resist these conditions. The carbon-hydrogen bonds, the guys down here, they are labile, they are reactive. So that tells me where the reaction is going to happen. It's going to be at a benzylic center, it has to have a benzylic CH, and I'm going to remove that and install a bromine. So the product from this reaction is going to be my aromatic ring. The tertiary butyl group remains untouched. Nothing's going to happen to it. None of these methyls are going to get touched at all. Nothing wrong there. The other center is going to have a CH removed, and I'm going to get a bromine. That's what I'm trying to make from this kind of reaction. That's what you'd be aiming for. What do you think would happen, though, if I took this molecule and I just wait longer with more NBS and more time? Are there more CHs on the benzylic center? Yeah. This can still make, you can still make di-substituted, 2 bromines, and then tri-substituted, 3 bromines. It will continue along. And it is kind of one of those things that each time you add a bromine, just like we did with things like the haloform reaction, right? Alpha bromination at the center with the base, the products are actually a little bit more susceptible to that CH bond cleavage. By adding these bromines in there, you're actually making the product a little bit more reactive. So this is one of those cases. It's a classic kinetics problem for new process chemists. Take the benzylic methyl, only hit it once, and stop the chemistry there. Designing a process around this does become kind of tricky. So generally, what we're trying to do, if we're asked to, say, predict the product, we're usually trying to hit the first bromine. That's fine. The thing I'm mentioning to you guys is it's possible to do multiple brominations, but that requires more NBS and more time in order to sort of decorate it. OK. So once we've got the benzyl bromide in place, the reason we do this is because we're taking what is kind of a boring benzylic CH, I'm turning it into a benzylic bromide. This is now a really good electrophile. We've installed the bromine because usually this is our ability to take a carbon hydrogen and turn it into something that's now a good SN2 target. So this lets me take molecules that have these benzylic methyl centers or methylenes, the CH2s. I can install a bromine in there, and this allows me to conduct synthesis where I come along with some other nucleophile, and I'm going to do displacement. That nucleophilic substitution, yes, it's a secondary center, but it reacts almost as fast as a primary. Because once again, the stabilization I have there, if I eject that bromine or the relative carbocation-like center I'm making here, this isn't just like a secondary carbocation, it's a stabilized secondary carbocation because of that adjacent aromatic ring. So it allows us, it's a very good opener to attach large fragments to other points. And again, you can brominate selectively at this alpha center, and then you use it in an SN2 chemistry for some other subsequent step. All right. So we're going to ask you to go through, start from toluene, and go make a final molecule. This allows us to do many steps for transformations. Now the next reaction, again, focusing on benzylic centers. Because those benzylic hydrogens are somewhat reactive, the next reaction we can use is oxidation. So this is back to our chromium reagents. This is something where I can use the chromium reagents, like Jones type reagents and stuff. I can do oxidation there, but what I'm doing is not just removing those hydrogens. And remember what we talked about oxidation. Oxidizing a carbon center means removing carbon-carbon or carbon hydrogens and adding in carbon heteroatom, carbon oxygen, or carbon bromine, or carbon nitrogen. So this is an oxidation reaction where we're going from something over here, which are primarily CH3, and we can actually stitch it all the way up to the carboxylic acid. I'm removing every single carbon hydrogen to make carbon oxygens. There is no stopping. If you take a chromium reagent and you do this, you're going all the way to the carboxylic acid. You can't stop at alcohol. You can't stop at aldehyde. It will rip through all parts of it to get to your carboxylic acid. Now, that's if you can remove these carbon hydrogens. Unlike in bromination, carbon hydrogens are in play. So is carbon-carbon. You take a molecule like this, and you completely delete the entire carbon fragment. You're taking the benzylic center, you're removing those carbon hydrogens and the carbon-carbon bond. Same thing here too. I can start with carbon hydrogens and carbon-carbon, completely deleting it. So the thing I'm emphasizing here is, as I have 3 different starting materials, that just because of this oxidation, I can completely reformat all 3 of these, toluene and the other 2 substituted ones, as benzoic acid. I completely can cut the other part off it. Now to get this going, you absolutely need at least 1 CH, but after that, you can chop it down completely. Because what you're doing is you're making a carbon-centered radical, oxygen comes in, and then you're just fragmenting it at that point. Yeah? In the end, it's kind of, nobody talks about what happens to that part of it. It does come in carboxylic acid, but this is really aggressive. You're chewing that part up, and it probably eventually becomes CO2, honestly. So you're probably you're doing pyrolysis of that part of the carbon skeleton because it becomes an uncontrolled sort of decomposition of the CO2. So they're not usually isolated because they're just gone up as gas or some other smaller fragments. Depending on the conditions, it can be things like ethylenes and stuff too, but they're really, really destroyed. You're not recovering that part of the molecule. Any other questions? So again, this is one of those great resets. Now, think back. Remember on the reduction side of the things, there was a reagent I told you guys was the great reset. It's a hydride reagent that takes any carbonyl and just deletes it. What was it? Lithium aluminum hydride. This is your other side. This is your oxidative great reset. You can take a benzylic center, I don't care what's attached to it, and you can delete it to become the carboxylic acid. So these are the molecules we're going to ask you to go through and predict the products from these ones. Now, last one is, let's say you did the Williams synthesis. This is now a molecule. Oh, sorry, yeah. Oh, a double bond in this position? You would actually do oxidation additions, right? So a double bond there, this is epoxidation, or closer to like epoxidation chemistry. It's not the exact same. I don't know what would happen if you push it hard enough. I would put that in the category of probably don't try to do it. I'd have to look up if it would actually eventually lead back over here. Remember, double bonds in this case with some of these conditions become like oxygen atom transfer reactions. Hydroxylation, dihydroxylation, and epoxidation. So that's more like the 203 sort of like hydrobromination and epoxidation chemistries. So usually we're only applying it when we have sp2 centers alpha there. So this is now if we have benzylic ethers. So remember, we talked about Williamson ether synthesis took a phenol where the oxygen was directly attached to the aromatic ring. We're walking out the oxygen one further. So this might be the product where what we did is we made a benzylic bromide first, and then we attacked it with an alcohol to make these kinds of ethers. So these are what we call benzylic ethers, right? Because it is at the benzylic position, we have our ether extending. Now, once we have these are useful because this is our way to protect alcohols. If I had an alcohol and a benzylic bromide, I can make my benzylic ether. If I want to get my alcohol back, one of the things it's very useful is these benzylic ethers are susceptible to hydrogenation. So what we can actually do here is I can take a benzylic ether in the presence of palladium over carbon and hydrogen, and what I'm doing is I'm fracturing this carbon-carbon bond to install hydrogen, so I'm reducing it to give me back a free OR. So this is what we would usually use as a protection group chemistry. If I had some way where I had an alcohol that I would just want to temporarily mask, I might use something like a benzyl bromide to make this kind of benzylic ether. I do a bunch of chemistry. The oxygen is no longer nucleophilic because it's not this OH alcohol. And then when I want to get back my alcohol, I can hydrogenate it. This is, again, one of those cases that up until now, hydrogenation is primarily used to functionalize carbon-carbon double bonds. This is your first example where what you can do is actually fracture a carbon-oxygen bond, but only works at benzylic centers. It only happens if you've got this kind of part here. I will show you guys the mechanism for how this part works because it kind of takes advantage of this double bond or the aromatic type character. It only works because of having that aromatic group adjacent to it. So, wow, we are very early today. So we can work through one of these if you guys want, or we can say it's Friday, enjoy the sun. Enjoy the sun. Okay, see you guys.
Okay, for our problems. First one here, we're asked to find the major product, organic product from this transformation. Remember, we're using a weak base, like potassium carbonate, and we have an acidic proton here. This is our standard ether formation where acid-base reaction is going to generate our nice stabilized alkoxide, this phenoxide, and then that's going to act by an SN2 reaction to give us our substituted product. So we're just adding the alkyl group as an oxygen nucleophile to this material. Doop, doop, doop. And so you can see there's 1, 2, 3 carbons like that. But this carbon here corresponds to that carbon there. For this next problem, we're asked to do the unstitching reaction. So this is how we cleave these phenolate or phenol ethers. We're going to do it under strong acidic conditions with something like HBr. And the mechanism, this is where we have very acidic protons in the system, right? HBr is a very strong acid. This will go an acid-base reaction to protonate at our ether. So this is kind of like SN1 looking thing. We're protonating this to make it into a better leaving group, and we have our methyl group. What's going to happen is after our first step. And the first step makes this compound. Second step, we're going to take our bromide, use that as a nucleophile to actually break this bond. Now it's probably going to look more SN2-like, just because otherwise we'd have to make a primary carbocation, but that gives us our molecule called catechol. It's this 1,2-diphenol. So that's our catechol molecule, and we're going to have methyl bromide as the rest of the material from this. So here we're asked to make benzaldehyde from toluene. So first thing we have to do is let's redraw those two pieces. Toluene is just benzene with a methyl group attached to it. Benzaldehyde has an aromatic group and then an aldehyde attaching on. So you can notice, again, if we're doing a synthesis, this carbon is probably this carbon here. The ring is probably the ring. So the major transformation we're doing is we're taking these hydrogens and we're going to cut them off to put a carbon-oxygen double bond in place. So how we're going to do this, step one, we have to functionalize it. This is where we're going to use something like our NBS with like a radical initiator. So something like our benzoyl peroxide or something to that point too. So it's our BN peroxide. And then probably heat. What this is going to do is we're going to make our alpha benzyl bromides. We've replaced one of those groups with a Br. Now that we have benzyl bromide, we need to install an oxygen function. So we're probably going to do that with something like sodium hydroxide. What that's going to do is we're using hydroxide as our nucleophile to give us our OH. And final step over here, this would be something like pyridinium chlorochromate, something that's going to oxidize only this primary alcohol up to a aldehyde. Okay, so for these, we're going to be doing an oxidation with chromic acid. Remember what that does is, first of all, we have to target benzylic centers. So I'm just going to circle all the benzylic centers seen here, like that. Now, more importantly, the benzylic centers need to have at least one benzylic CH. That's what we need to sort of bite into the molecule in order to start the oxidation reaction. So these have 3, there's 2 over here, there's 3 over here, and this one does not have any. So that one is just going to be resistant to this transformation. Remember, when we attack that center, what we're going to do is remove all CH or CC bonds at the benzylic center. So this one is going to cut down to benzoic acid. So we're completely transforming that center to the highest oxidation state. This one, both of the centers can be susceptible, again, cleaving all of the hydrogens and carbons, so carboxylic acid there, as well as a carboxylic acid over here. Both are possible. And then the last one, 2 of them are susceptible, 1 is not. So this methyl will become a carboxylic acid. This group here becomes a carboxylic acid. This one is untouched. Since we don't have one benzylic CH to start the reaction, it's actually resistant at that center and so is not touched. So if we're going to do this reaction, what we want is a reaction where we're going to do a hydrogenation of this molecule. So we're doing hydrogenation of this molecule in the presence of our benzylic ether. So when you do this, take a look closely. What we're looking for is an aromatic group and a benzylic center. That's the minimum piece that we need to do our reduction on. What that's going to do is it targets this carbon-oxygen bond attached to the benzylic center. That's going to be the center we're going to cleave across here. The rest of the molecule is not touched. So under hydrogen and palladium, we're targeting this benzylic ether, this carbon-oxygen bond attached to the benzylic center. That's going to give us this fragment here as the alcohol. Remember, hydrogenation doesn't really impact esters. It's really targeting things like carbon-carbon double bonds. If we wanted to do something else like targeting the ester, we use sodium borohydride instead. what that leaves you is this fragment. That's our phenol and carbon. So this piece here becomes our toluene fragment, or just methylbenzene at that part too.